Good morning, everyone. A very good morning. Shall we begin the session? Yes, today's topic is the chapter number 6, that is the formal relational query languages. That includes a non-procedure languages. That includes a procedure. Non-procedure means whatever the procedure, whatever the terms that we are introduced in the relational model, and that also covered in the SQL in the great detail. In this chapter, we present the formal model that depends upon which SQL as well as relational query languages are based. So we cover three formal languages. We start by presenting the relational algebra, which forms the basis of the widely used SQL query language. Then we use the tuple relational calculus and the domain calculus that is used for the query languages, that is used for the domain relational calculus, that is the declarative statement, that is a use statement that uses the relational algebra, which forms the basis of the widely used SQL query language. Then after this, we also cover the relational or the tuple relational calculus and the domain relational calculus, which are declarative in the sense which are declarative based on the mathematical logic, whatever the mathematical logic we are using. So whatever the logic, whatever the behavior we are using, that is introduced with the relational algebra, that is used in this chapter, that is also known as the formal, or that is also known as a formal model that depends upon which SQL as well as the relational query language are based. So we cover at most, or we cover three formal languages. We start by presenting the relational algebra, which forms the basis of the widely used SQL query languages. Then use the tuple relational calculus, then the domain relational calculus. So one is the relational algebra, one is a tuple relational calculus, one is a domain relational calculus, which are declarative language. The next one is let's start with the first one, that is a relational algebra. So this is the procedural query language, and this language is used with the declarative, how it is used, or what are the various procedures that we followed up, that consist of a set of the operation that takes one or two relation as input. So this is the procedure query language that takes one or two relations as an input and produce a new relation as their output. So that means it takes one or two relation, one or two table as an input and produces a new relation as their output. Output in the sense whatever the, yes, what is the outcome. Then the fundamental operation that is used in the relational algebra are the select, project, union, set difference, Cartesian product, and the rename. These are the six relational algebra operations. One is a select, one is a project, one is a union, one is a set difference, one is a Cartesian product, one is a rename. And in addition to this, there are several other operations also, that is known as the set intersection, natural join, and the assignment. And we shall define these operations in terms of the fundamental operations also. Now let's start with the fundamental operations. So first one is a unary. So select, project, rename operations. That is the three operations. One is a select, one is a project, one is a rename, that are known as a unary operations. That means they operates on only one relation. Other three operations that operates on a pair of the relation. Pair of the relation means there are multiple relations, there are multiple or the combined relation, more than one table that is used, that are known as the binary operations. Yes, select, project, rename, unary. Other operations, okay. Other in the sense union, set difference, and the Cartesian product, that are known as the binary operations. Yes, let's start with the first one, that is a select. So till now we have studied about that is a what is a relational algebra, how it is used, and there are six operations. There are six operations that we use. One is select, then project, then union, set difference, Cartesian product, and rename. And other operations also, that is a set intersection, natural join, assignment. So first one, or the select, project, rename are unary, and the other one, that is a binary. So let's start with the first one, that is a select operation. So this is a select operation, select the tuple that satisfy a given predicate. This selects the tuples, this selects the rows that satisfy a given predicate in the sense outcome. We use the lowercase Greek letter sigma to denote selection. So we use a sigma for the select operation, and the predicate appears as a subscript to the sigma. Argument relation is in parenthesis after the sigma. Therefore, To select those tuple of the instructors, this is the one of the example. So if I want to select all the tuples or those tuples of the instructor where the instructor is in the physics department. So what is the criteria? We can say what is the condition that is the instructor is in the physics department. So we write sigma department name equals to physics instructor. And if the instructor relation is shown in this one, this is a table that's shown, and whatever the physics department. So if I'm talking about the physics department, this is one, this is two, this is only two. Two outcomes are there. Department name is physics from department. So we are getting out all the rename that is given out. Yeah, this is the outcome. There are only two department physics. One is the IDs of the physics instant 95,000, gold physics 87,000. So this is the result of the sigma department name equals to physics instructor. And if the instructor relation is shown over here, then the result will be shown in the figure 6.2 we have studied. Now, we can also find all the instructors with salary greater than $90,000. Now, we have to find out the instructors whose salary is greater than 90,000. This is the scenario. Salary is greater than 90,000, not equals to, greater than. This is not available, this is not used, this is not used, but this is used. So this is the first part. Then this is not, this is not, this is not, this is not, this is the second part. Only two rows are available for this. One is a 95,000, one is a 92,000. That is the instant and the branch. This if we also allow the comparisons with using the various operator, that is equals to, not equals to, less than, equals to, greater than, equals to in the selection predicate. Furthermore, we can also combine several predicate into a larger predicate. That means we can take the conditions, we can combine the conditions by using the and, or not. Therefore, to find the instructors in the physics for salary or with a salary greater than $90,000. Physics also, salary also. So there are two conditions. So we use either or and. This is department name physics or salary is greater than 90,000. That is either physics, either 90,000. So in this, there are four outcomes. Why? Sorry, three outcomes, because physics are the same department having the salary 95,000. In the same way, physics have another salary. This is a salary for the 90,000, 95,000, but this is a physics, this is a physics. Next one, physics is 87,000. Next one, 92,000 is computer science. There are three rows. One is a instant, one is gold physics, one is brand computer science. There are three rows over here. So selection predicate may include comparison between two attributes, and to illustrate, consider the relation department, and to find all the departments whose name is same as their building name, we can write department name equals to building department name. So SQL versus relational algebra. So the term select in the relational algebra have a different meaning than the one used in the SQL, which is unfortunate historical fact. And in relational algebra, the term select correspond to what we refer to as SQL as where. So we emphasize the different interpretations, how to minimize the potential confusion. Now we have done with the select. In this, we have to choose the tuple. We have to find out the tuples. Now next is the project. Suppose we want to list all the instructors. So this produces the relation, but do not care about the department name. We only care about the ID, name, and the salary. So in this, we are specifying the columns, but in select, we are specifying the condition that gives the output as a tuple. So select works on the tuples and the project works on the columns. So suppose we want to list all the instructors, that is the ID, name, and the salary, but we don't care about the department name. So the project operations allows us to produce this relation. And the project operation is a unary operation that returns its argument relation with certain attributes left out. And since the relation is a set, any duplicate rows are eliminated. So this is a set. So any duplicate rows, if there is any duplicate rows, that are eliminated over here. And the projection is denoted by the uppercase Greek letter pi. We list those attributes that we wish to appear in the result as a subscript to the pi. So the argument relation follows in parentheses. So we write the query to produce such list as pi, ID, name, salary, instructor. So we are taking out only three fields. One is the ID, one is the name, one is the salary from instructor. Now next is the composition of the relational operations. So fact is that the result of a relational operation is itself a relation. That is very important. And consider the more complicated query. Find the names of all the instructors in the physics department. That means we have to find the names of each and every instructors in the physics department. So we write ID name salary 10101 Srinivasan 65,000, 12121 WU 90,000, then and so on. So we write the instructor, we write the query of this one. And notice that instead of giving the names of a relation as an argument of a projection operation, we give an expression that evaluates an operation. So this gives the output as a relation, this gives the output as a table. And in general, since the result of a relational algebra is of same type, that is a relation only as it is in input. So relational algebra operation can be composed together into a relational algebra operation or expression. Then composing the relational algebra operation into the relational algebra expression is just like composing arithmetic operations such as plus, minus, divide, multiply, addition, subtraction, division, multiplication into the arithmetic expression. So we study the formal definitions of relational algebra that is used over here. Next one is union operation. So consider a query to find the set of all the courses taught in the fall 2009 semester to the spring 2010 semester or both. So the information is contained in the section relation. To find the set of all the courses that are taught in the fall 2009 semester, so we write pi course ID. So we are fetching out only one column. What is the condition in that column? Semester equals to 4 and year equals to 2009. How do I know this is and? Because this is given over here. This is and or not. V is or, reverse V is and. So semester is false and the year is 2009. Both the conditions satisfied. This is the how the all the courses are taught in the fall 2009 semester. Next, to find all the courses that are taught in the spring 2010 semester. So one is spring 2009 semester, one is spring 2010 semester. So we write pi course ID, then sigma semester equals to spring and year equals to 2010 section. So to answer the query, we need the union of these two sets. That is, we need all section IDs that appears in either or both the two relations. So if we find these values, that is the BIOS 101 section ID semester year building room number time slot ID. That is given within the binary operation that is denoted in the set theory by U. The expression needed is pi course ID semester 4 the year 2009 section union. That means combination of both the value, then course ID semester equals to spring, year equals 2010 also from the section. So the result relation for this query appears as follows, and notice that there are 8 tuples in the result, even though there are 3 distinct courses offered in the fall 2009 semester and 6 distinct courses offered in the spring 2010 semester. And since relations are sets, so duplicate values such as the CS101 that is also offered in both the semesters are also replaced by the single occurrence. And observe that in our example, we take the union of two sets, both of which consisted of the course ID values. And in general, we must ensure that unions are taken between compatible relations. For example, it would not make sense to take the union of the instructor relation and the student relation. And although both relations have 4 attributes, they differ on the salary and the total credit domain. And the union of these two operations or attributes would not make sense in most of the situation. Therefore, for a union operation, RUS to be valid, we require two condition hold. What is the condition? So the relations R and S must be of the same R-tree, must be of the same domain, that is, they must have the same number of the attributes. The domains of ith operation or attribute of R and ith attribute of S must be same for all. And R and S can be either database relations or temporary relations that are the result of a relational algebra expression. Next is the set difference operation, that is denoted by the minus. So find all the tuples that are in one relation but not in the another relation, that is done by the set difference. So therefore the expression R minus S produces a relation containing those tuples in R but not in the S. This is a course ID CS347 PHY101. So we can find all the courses taught in the fall 2009 semester but not in the spring 2010 semester by writing pi course ID semester equals to 4, year equal to 2009. Pi course ID semester equals to spring, year equal to 2010 section. And as with the union operation, we must ensure that the set differences are taken between compatible relations. Therefore, for a set difference operation R minus S to be valid, we require that the relations R and S of the same R tree and that the domain of ith attribute of R and ith attribute of S be the same for all I. The next one is a Cartesian product operation that is denoted by the cross, that allows us to combine information from any two relations. That is the Cartesian product. So we write the Cartesian product of the relation R1 and R2 as R1 into R2. That means each and every attribute, each and every column of first table is combined with the each and every column of the second table or attribute of the second table. And recall that a relation is by definition as a subset of a Cartesian product of set of domains, and from that definition we should already have an intuition about the definition of the Cartesian product operations. Now let's start with the Cartesian product operation that is denoted by the cross, that allows us to combine the information from any two relations, and we write the Cartesian product of a relation as a R1 into R2. And recall that a relation is by definition a subset of a Cartesian product of a set of the domain. And from that definition, we should try already, or we have an intuition about the definition of the Cartesian product operation. However, since the same attribute may appear or name may appear in both R1 and the R2, we need to devise a naming convention to differentiate between these attributes. That may be an instructor, that may be a relation, that may be a attribute that is originally come. For example, the relation schema for R, that is instructor and teachers, that is instructor.id, instructor.name, instructor.department name, salary. So there are four fields from the instructors: ID, name, department name, and the salary. Then from teachers, ID, course ID, section ID, semester, and the year. With this schema, we can distinguish instructor.id and the teachers.id. And for those attributes that appears as a part of two schemas, two table, we shall usually drop the relation name prefix. This simplification does not lead to any ambiguity, but we can write the schema or relation schema for R as instructor.id, name, department name, salary, teachers.id, course ID, section ID, semester, year. And this naming convention also requires that the relations that are the arguments of the Cartesian product operation have distinct name, and this requirement causes the problems in some cases, such as when the Cartesian product of a relation with itself is desired. In the same way, there is a problem that arises if we use the result of a relational algebra. So we shall need a name for that relation, so we refer as a relational or a relations attribute. So we will avoid these problems by using the rename operation. So we use the rename. What tuple appears in the R, what we construct of the R, that is a possible pair of the tuple, one from the instructor relation, one from the teacher's relation. So R is a large relation, so we can see, which includes only a portion of the tuple that makes up a R. And assume that we have n1 tuples in instructor and n2 tuples in teachers. So this is defined with the n1 multiplied by n2 ways of choosing a pair of tuples, one tuple from each relation, so that n1 into n2 tuples in R. And in particular, note that for such tuples in R, it may be that T instructor ID is not equal to T teachers ID. And in general, if we have a relations R1 and the R2, then R1 into R2 is a relation whose schema is a concatenation. Concatenation means combining of the R1 and the R2. And the relation R contains all the tuples T for which there is a tuple T1 in the R1 and tuple T2 in R2, for which TR1 is equals to T1 R1 and TR2 is equals to T2 R2. And suppose that we want to find the names of all the instructors in the physics department together with the course ID of all the courses they taught. So we need the information in both the instructor relation and the teacher's relation, that is as follows. To do so, and we write department name physics instructor into the teacher. Then the result is the relation that is expressed in the figure 6.9. So we rename instructor ID to reduce the width of the table. So there's the instructor.id, name, department name, salary, teacher's ID, course ID, section ID, semester, and the year. So we have a relation that pertains only to the instructors in the physics department. However, the course ID column contains certain information about the courses that we are not taught by the corresponding instructors. Such Cartesian product is that associate with every tuple of the instructors, every tuple of the tables that associated with the teachers. Now this is one of the example: instructor.id, name, department name, salary, teacher's ID, course ID, section ID, semester, and the year. This is including with the department name. This is including with the physics, with the teacher's instructor that contains his name and which satisfy the instructor.id, that is equals to teachers.id. So if you write instructor.id, teachers.id, department name, physics, instructor, teachers, so we get only those tuples of instructor and the teacher that pertains to instructor in the physics and the courses that they taught. And finally, we also say that we write the names of only those instructors, all the instructors in the physics department together with the course ID of all the courses that they do by using the projection. This is by name, course ID, instructor.id, teacher.id, department name, physics, and there are two tables, instructor and the teachers. And the result of this expression is the correct answer to be observed as a query, and although that gold is in the physics department, does not teach to any course and therefore does not appear in the result. And note that there is often more than one way to write a query in the relational algebra. Next is the rename operation.